Good evening, friends. Welcome to Eastern Academy, and we are discussing about electronics. And this is our session 4, and this is part of our embedded system programming. And we are continuing our discussion on types of transistors. So the last session we discussed about NPN and PNP, and the other types we'll discuss on this session. It is extended more than what I expected. That's fine. We'll continue on this. Okay, so the PNP and the NPN. Okay, the problem with what they found in the industry is this. Either IB have to go this way, the control current, or the control current of IB. Both of them are IB, the direction is different. Either it goes from base to emitter or emitter to base. That doesn't matter. But the same effect is same. IC is equal to beta into IB, IC is equal to beta into IB, everything correct. Here the current will flow like this, here the current will flow like this. Okay, they're all different applications we use it. But here is the problem. The problem is this guy. When I have multiple huge number of transistor circuits, the control current become too high. So people are trying to find out how to reduce that. They found out a nice device. Actually, to be frank, that was invented before that. That is actually called voltage controlled device. That is called voltage controlled device instead of current controlled device. Here we are using P and N material. That's why they call this as a bipolar transistor. Bipolar junction transistor. There are two junctions. But the other one, they have done a superb idea. Think of it, 1 minute. This is the trick you need to understand. I have a silicon atom. I add a boron atom. I have a silicon atom. I add a phosphor atom. I get here a material, new material called P material, because it has 4 plus 3. It becomes 7 valence electron. But it is not positive, as I told you that. This is a very, very stable atoms. But this one is silicon plus phosphor. It's called N material. You have extra electrons. 7, 8, 9. That is 5 plus 4 plus 5, 9. So 8 the orbit and 1 in the final orbit. Or if you do the bonding, one will be outside. That's fine. That's I'm not a chemical bonding lecturer. That's that you have to go in depth. Somebody else. If you want to understand this in very depth, I'm not a guy. I stop where I stop. So I get now two new material called P and N material. They are not positive and negative material. Now let us assume that I have a P material, or let's say I have a N material, and I apply a voltage here. What will happen? When I have a N material, I have a voltage. What will happen? I have a bulb. Understand what will happen? Let us discuss this first. I have a N material. I have a N material. I have a bulb. What will happen now? What will happen now? This is a superb conductor because it has a valence electron. So what happened? The electrons will start flowing this. Okay, the current will flow like this. So bulb will glow. No control. Now, what they have done, a small trick here is this. I make a small dielectric here. Understand? I make a small dielectric. That means that this one, okay, this area, and I have a small dielectric here. They do not have a contact. This is conductor. This is conductor. Okay, this is dielectric. Let us assume that. Let me make a different color. Okay, so these two don't have any contact. This N material and this material. Let's take this a P material. They don't have any contact. Yeah, there is a dielectric. Forget about it. I'm not worried about the what is the value of K and all. It's a dielectric. So that will split both. So when I don't have, if I don't give any voltage here to both, that is 0 volt. Okay, there is no effect. This is going to pass the same current. Everything is going to be right. So when I give a 0 voltage, and the current is going to flow, nothing is going to happen. Am I right? Now, when they give here 5 volt, what will happen? When they give here 5 volts, what happens? This guy is positive. Am I right? So this guy is attract all the electrons, and here all the other will be positive. Everything will be positive. And here also will be positive. That will attract all the electrons hereby. But this is a dielectric, that is insulator. So no current will flow. No current. Please understand. No current. But what happens? All the electrons will be attracted by this guy. These two elements. Because of that, this space become no free electron. No free electron. Because of this no free electron, the movement is blocked. So the bulb is going to be off. You understand now? What happened? As long as there's an electron here, there'll be a movement here. If the electrons are attracted by this acts as a capacitor. Please understand. I did not tell you that this acts as a capacitor. This is a conductor, and this is a conductor. Now, if we have a dielectric, Dielectric is an insulator. Please understand, when I say dielectric, that's an insulator. Okay. So please understand the property of capacitor is, if you take the capacitor, it attracts the electron, but there is no current flow through the electrons. Am I right? Because this in between is a dielectric. That property they used here. That is the beauty of this device. But the effect here, you're applying the voltage, this current is controlled here. The current is controlled here. Because of this, the current is controlled. Once again, this is nothing but, once again, it becomes a variable resistor. Because if we change the 5 volt to 3 volts, less current. 2 volts, more current. 1 volt, 0 volt, more current. So based on your this one, voltage, this is, they call this a gate. Like that in the thing we call base. Here they call gate. And that we call this is collector bar in your BJT. And here they call drain. Drain is the one which collects. You know that. See, both the same name, but they wanted to differentiate that. If I say drain, if I say gate, you know that it's called FET. Correct, exactly. When you increase the voltage, the current will be less. To want a more deeper understanding, I'll refer a book. You can understand that. Okay, then we can discuss if you want later. If some of you wanted, I'm giving you the idea now. See, basically, please understand. Idea of top level is very important than to go into the too technical. First of all, you should know that what is the difference between current controlled and voltage control. How that is guy is controlled. What are the advantage and disadvantage? Then go in deep. Then go in deep. I will share the analog electronics videos. Okay, I'll share today itself. If somebody is interested, then let me know. I'll share the analog electronics videos. That I've discussed more about this. The classes. You can watch the analog electronics videos. I'll share it. Okay. That I discuss about the application of amplifier, how the amplifier works, how the regulator works, and everything. So is it clear now? So please, the same name in BJT we call it as a collector. Here they call drain. In the voltage, what we have given there in this one, BJT, we used to call VCC. Here, this is drain. We call VDD. Both are same. Yeah, it's all uploaded. I have to share the link only. All the analog electronic videos are uploaded, which you will get this one. Okay, I'll just send you the link. I don't give it to everybody. Those who are interested only, I'll give it. Otherwise, many people don't like to get into the analog electronics. That's a more different way of approach. Now, this one they call source, which is actually called emitter. See, if you see the difference here, source and emitter are same. This guy emits, this guy is sourcing. That guy is collecting, that guy is draining. This guy is base, and this guy is gate. They put a symbol like this. They put a symbol like this. Okay. This is called gate, source, and drain. And this gives you exactly the capacitive effect. This one. Okay. This is called actually this is called field effect transistor. Why they call field? The field effect is, the field is a one, the electric field generated here is controlling the flow of electron. This is actually electric field. Base means it is BJT. Base is BJT. Volt gate is FET. Source is FET. Emitter is BJT. I'm trying to compare both. Okay. The BJT is a current control. Current have to flow through between base and emitter. Otherwise, there is not be any current. But here, there's no current. You apply only a voltage. The voltage is going to take place. So if you compare these two, that is, one is FET, BJT, other one is FET. Here it is emitter, base, collector, source, gate, drain. Understand? And here you have two methods. In the BJT, you can have either like this, P, N, P, or N, P, N. You can form two-way. So this is, we have inside arrow, because PN goes like this, forward bias, and NPN is like this. I don't know. When I have a time, I'll make few videos of applications of this. Why it came. When you have since somebody is, a lot of people are now first year students, they're all very good. They'll be able to understand these things when they have a time. I'll slowly make one by one how they are used as regulators. Normally, final year students, I don't teach much about analog, and those who are doing job seekers, because they are not in the mood to learn. They're in the mood to get a job. But first year, second year students, this will be very good. I'll try to give them more videos and update you. But this is sufficient to understand about microprocessor and the embedded system. That is, I know what I'm giving you is a sufficient condition, but not in depth. But I can discuss about in depth later. That will give you the good idea for you. So now, in the FET also there are two types. I can have N material, or I can have only P material. This is called N channel. This is called P channel. But they want to differentiate also. See here, they have to differentiate. They put a symbol, this is for FET. Like this is for transistor. This is for transistor. But they differentiate by arrows. Here also they differentiate the arrows. But here there's no current control. But still, they make a small arrow change here. That is, if you make the arrow inside, okay, then it's called it as a P channel or P channel. The arrow outside, they call N channel. Sorry, I did a wrong here. I changed, sorry, I put arrow outside for N channel, arrow inside for P channel. I didn't know the top one. That's a mistake. So this is quite simple concept, not as complicated this. This is a simple conductor. By controlling using the capacitive effect, I was trying to remove the either hole or here's a hole here. We attract all the holes here, though the center ports, there's no conductive path. Basically, I'm making the more resistive path or insulator. That means that if I don't have any free electrons, that's called insulator. I mean, that's what I'm doing here. I do not make any free electrons. And here also, we make all the holes attracted here by applying the voltage here on the N material. We don't do that. That's a very top level principle. Understand that. That's the most important thing you have to understand. The top level. Now it's fine. They were very happy this. But they faced one problem. What is the basic difference between these two? This looks to be very advantageous because we don't give any current here, but we are controlling the current. But here we are giving current. So this is taking more current, this is giving less current. But you need you need to understand one main property of capacitor. When there is a dielectric and capacitor, there's a big property. What is that? What is the problem? What is the problem with the capacitive thing? There's a big problem. That is called charging and discharging time. So it takes more time for charging and discharging. Understand? It stores the charge. That's fine. But for storing, it takes time. Whereas your this one, what do you call it? Transistors, bipolar, there's no storage. So the electron flows very fast. So this always BJT is fast. This one is slow. This one is slow. Understand? So BJT is fast. Which one is slow? FET is slow. But the advantage here is this guy takes more current. This guy takes less current. So people are very happy to use the FET. This usage is almost gone. Now they have faced one more problem. The problem is this dielectric. The dielectric, they wanted to make a dielectric such a way that it is too thin, such a way that it will attract all the electrons, and that will be a perfect insulator. This should be a perfect insulator. At the same time, it should be thin. Finally, scientists found a nice method. What they found was, this is silicon, am I right? What they done, SiO2, silicon oxide. Silicon oxide, they used as a dielectric that has been very powerful. It gives you very, very thin, and at the same time, it was a perfect insulator. It becomes short means that become waste. The transistor is gone. So they made a perfect insulator. That's why they call this as when they start using this, they call this a MOS FET. What is MOS? Metal oxide. In this case, metal means silicon. Silicon oxide, they call it a metal oxide. That's a trick. Sometimes people ask me that, sir, what is called bare metal software? There's nothing called bare metal software. Your software directly runs on microprocessor. It's called bare metal. So what is the FET is there? So metal oxide semiconductor field effect transistor. So this is actually is a MOSFET. Understand? So what is the advantage of MOSFET was they had thin dielectric, very, very thin dielectric. So they could be able to do that. So to differentiate between the FET and MOSFET, they have just included one more arrow here. This is called P channel and N channel. So as we discuss the thing here, we had PMOS, NMOS. Nothing. PMOS means we have a P channel. The terminologies, I'm trying to introduce the terminologies. N channel. That means that the N material and P material. And I have the same concept here. There's no change. Of course, they are saying a lot of new transistors. I'll tell you the why this field has gone so popular. Nowadays they put the ICs. That is what I want to discuss about in the implementation today. I'll have a class on maybe this. I'm not at plan now. If I don't have any other session, I'll try to have it a class on Saturday. One session on the implementation. That will be very nice. How these are all these technologies are implemented. That I want to discuss on this session. That how they are doing it on the ICs and everything. That is very important. In electronics, you should understand about implementation of circuits. So these are all components. So what I'm doing is here is you understand once again now, very simple. I have a black block. This is a main circuit. This is controlled. In this case, gate is controlled. And this is main. Drain and source. This also can be like a switch or a regulator or a variable resistor. So they have a problem. The problem was this guys charging and discharging takes time. So it means that I change this one to 0 to 1 or 1 to 0. It takes some time. So they thought, how do I change this mechanism? What they have done was superbly. See here, there's a switch here. There's a switch here, two switches. This is the output. Understand? There are two switches. Okay. And this is a control. I have two control. If this switch is on, when I give 0 voltage. When I give 5 voltage, the switch is off. 0 volt means on. Understand? 5 volt means off. This switch, when there's a 0 volt means off, 5 volt means on. There are two types, N channel and P channel. That's why normally they draw like this. P channel, they draw with a circle. That's the way they draw this. So that we'll discuss next. Now what happened? When I make this 0 volt here, this guy will be on. Sorry, off. And this guy will be on. So this 5 volt will go here. Understand? Same way, when I make this guy as a 5 volt. So let us take this connected here. The input. We call this as out. Understand? This is in, this is out. This is a block. See, first try to understand your logic, common sense. Then we will get into the transistor. If you don't understand this common itself, that's fine. That means that there are two blocks. This block is controlled by when 0 volt means on, 5 volt means off. This is when 5 volt is given, it's on, 0 volt is off. There are two types of FETs are there. MOSFET and PMOS and NMOS. We'll replace this with right FET. Okay. Now what happened? When this guy is, they give 0 voltage here. This becomes 0. So this is going to be on. So this becomes 5 volt. When I give 5 volt here, this is going to be off and this is going to be on. So the 0 volt goes here. So 0 volt means 5 volt, 5 volt means 0, 1. So this is called inverter. It's called inverter. What inverter? I use 2 type. Okay. This one, 0 volt means on. So this is actually what I use was PMOS. Here I use NMOS. But since I'm using both the MOSes, they are complementary each other. One is on, other one is not on. They call this as a CMOS. Complementary metal oxide semiconductor field effect transistor. CMOSFET. Understand what is the difference? CMOS is a wonder, not only here, they use different technologies. They use the CMOS to construct the AND gates, OR gates, all the gates. But the trick is here, they use both the thing. Why they use is, if you don't use this methodology, it will become very slow. When I change it from 0 volt to 5 volt, this guy will react very slow. Whereas when I make this guy, they will be acting it very fast. That makes the things input to output time. I know that I may not have gone in depth, but I don't have time to go very in depth. Okay. Sadly, I'm two reasons. One is also not in depth. One is other one also. I'm also not too good at this type of circuit analysis. I'm an embedded guy. Inverter function is, when I give a 0 volt, output is 5 volt. 5 volt means 0 volt. And as I told you that this is nothing but a switch. I'm acting them both the saturation as a switch. So now when I use 2 different type of MOSFET. One is PMOS and NMOS. This guy, when it's 0 volt, this is on. When it is 5 volt, this is on. That's the property. So that I'm using that. So when I apply 0 volt as an input, both are getting 0 volt, but this one is off. But this one is on. So I get the 5 volt here. When I apply 5 volt, this one is off and this one is on. So I get the 0 volt. Why people have done it? So many reasons. If you don't do this, the typical circuits will be like this. Normally, typical circuits will be like this. Typical circuit will be like this. If you use only one FET, if you apply 0 voltage, let us assume this is on, this is off. Let us assume that when I apply 0 voltage, this is off. Okay. So now, since this is off, you get here 5 volt. The same voltage comes here. So you will be drawing the current through this. So I square R. There'll be a heat power dissipation. That is nothing but a heat. That is nothing but a heat dissipation. That is very high. If you draw more current, there'll be more power dissipation. Okay. If you don't put a resistor, okay, then when I make this again as a 5 volt, this is on. Then this gave heavy current, this device will get damaged. So I have to have a resistor to do that. You understand now? If I give if I give 5 volt, this is going to be on. That time to control the current, I have to have a resistor. But if you put a resistor, when I give 0 volt here, this is going to be off. The output is going to be 5 volt. If somebody is going to draw the current, all the current go through the resistor. So I square R power dissipation. But in this method, by making it as a 2 FET, we had an advantage. The advantage is when they give 0 voltage, this is going to be on. When they give 5 voltage, this is going to be on and this is going to be off. Whereas the power dissipated on this thing is, yeah, power is I square R. That is what you are getting. This is what the power dissipation, all these things. If you have a resistor, let us say that you are running, if somebody stops you, you are wasting the power. For example, you have a car. Let us assume that you have a car. It's a smooth road. And there's a road with like this. Okay. This consumes less petrol. This consumes more petrol. Because this road, smooth road, gives less resistive, less friction. This gives you more friction. You understand? This gives you less friction. This is called more friction. Okay. When you have more friction, you waste a lot of power. You are wasting lots of energy. That is called power dissipation. So to control from 1 kilometer, from X to Y, if it is 100 kilometer, in this case, you will use only about 2 liters of petrol. In this case, you will use 4 liters. You waste more power here because of the road is not smooth, because the road is giving more friction, more resistive. Same thing here. If I have a path, if I have a more free electrons, if it goes the current, then this gives less resistance. So the power wastage on this area is less. Whereas if you have a less free electrons, then I have to give a more thing, then this gives you more resistance for the current flow, then that gives you the more power dissipation, more resistance. The same thing here. When you have a this one resistor, if you use the FET, okay, this gives you less resistive path, but we control it through this circuit. That is the reason they made this circuit. That is the reason. I'll come out with the reason now. That is what I want to discuss on implementation. That I'll scribe it down. How come they are trying to put 10 billion transistors in IC? Not even 10 billion. Nowadays, people have got to 100 billion. 100 billion transistors in a IC of such a small space. The bigger one is covered. The space area is small. You can find out that. Let me see that. What is the maximum density? Let us search now. 1 minute. Let me search. What is the maximum transistor available? They use it on this. Sorry, I have not shared it. Let me share it now. So let me search it. Maximum transistor density. This is called density. Oh, even there are some chips there. They put 100 million transistors in a single chip. That is fine. That is not the limit. Let me find the thing. It's Let me check 1 minute. Sorry, I wanted to give you the correct answer. That's why I want to give you the. I want to search and give you the correct answer. Let's see that how they are doing that. See here, commercial microprocessors in 2021. Okay, they put number of MOSFETs is 57 billion. 57 billions. And they also say that it is density is somewhere they mention. Of course, here they are mentioning you as a size 10 nanometer to 2 nanometer, and future is 1 nanometer. Right now, 2 nanometer is coming. It will come in another 2 years. So they don't mention that. I'll show you later. That is, the density is that in a square millimeter, how many transistors they put. Do they have anything here? Yeah, see here they have mentioned. See here, Intel first microprocessor is having how many transistors? 2,250, but the size is 12 millimeter square. But now they say that latest ones. Come down, come down, come down. See here, they are all 57 billion, and they have 432 millimeter square. Then you find out how much is the transistor they have it on per mm square. That is called the density. Okay, this is the size of process. I'm not going to go in depth. That we will discuss on implementation. Okay. No, what I'm trying to say is this: how this information, what I'm providing you, that is why the resistive path, what is the power dissipation. When I assume that you have about 1 million transistor, 1 million transistor, think of it, 1 million. If a transistor consume 1 milliwatt, 1 milliwatt, then think of it, it becomes 1000 watt. That's all your transistor will burn. Okay, because we are in embedded, we should know that what are the things happening, affecting our embedded systems. So nowadays they are putting 100 billion transistors in IC. Every transistor is consuming so much of current and so much of power I square R. Okay, then think of it. This many transistor into the power, the chip will burn. Now why it is not burning is, it's because of two reasons. One reason is, at a time we have only a few switches are on. So less current. Second one is, they reduce the I square R. That's the thing I'm telling you now. If you don't have the, so please understand, go back to electrical principle. You give a voltage here, you have a bulb. How come bulb is glowing? How come bulb is giving you light? How come your heater is working? These are all because they are giving friction to the current. They are giving friction to the current. You understand? That's the trick. If they give a friction, then that is called I square R. That is power. The power dissipation is a very big area today. That's why normally what you do is, when you do, this is a big, very big area today. You have in my embedded system, we have mode called sleep mode. If you put a microcontroller in sleep mode, that time it will consume less power. So you can use the battery for a long time. So power is try to understand. Don't leave now. You please go through about power and ask me any doubt about power. Right now, if I give a resistor, we pass through the current I, then the power dissipation is I square R. That is going to be the waste. Yeah, that is what I'm trying to discuss about on the implementation session. We will do it. That's why I told you I have a separate session for implementation. But since we have this FET and everything, I could not able to get into the thing. We will do it on the how we are fitting. This is a very, very good question. How we are fitting 100 billion transistor in such a small area of, let us assume that 20 millimeter by 20 millimeter. That is 2 centimeter by 2 centimeter. Think of it. Actual size is 2 centimeters, only this much. And this area, people are putting how many transistors? 100 billion. Am I right? This chip is out. This guy, what is that? Your iPad M1 chips or all Apple's iMac chip is only this much. This is becoming a common. Till 2 years back, 10 billion was common. Now 100 billion become common. If you get into the things, you can discuss so many things. But have your doubts, all your doubts, and compiled, and send me the questions. I'll try to give a video answer for everything. That will be useful for everybody. All your doubts, make it as a document and send it to me. When I have a time, I will create the answer for each and every question. I'll create a video answer. So people, it will be not only to you. A lot of people, those who are going for interview or trying to understand, that thing will be very, 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 very visible. Yeah, that I'll explain to you now. Oh, that's all. That is what our discussion. In the phone, the transistor used. Somebody has asked about what is the use of phone transistor in the phone. Transistor is acting as a switch. See, this is what the full flow of everything. We have electrical. There, we had a voltage, current, and resistance. The resistor can be a switch. Sorry, here is a switch. Control. Now, the switches can be automatic control. That is what digital electronics we call gate. This is used form AND gate, OR gate, NOT gate. Using this gate switch, that is transistor. Now from here we discuss create 3 logics: combination logic, sequential logic, and tri-state logic. From there we create ROM and RAM. And then we create microprocessor. This is what's used in your phones. You just go and watch the digital electronics series or attend next live session. You will understand the full flow. We have multiple flows. This is electrical session. This is electronic session. This is digital electronic session. And this is microprocessor session separately. We have so many sessions. So please understand this. What the biggest advantage of FET is? 2 reasons. One is less current. Now with the help of CMOS, they make it speed. But still this speed is slower than BJT. But we cannot use that BJT because if you put the 10 million transistor or not, BJT is gone. It consumes too much of power. Every base current is consumption. So the CMOS we use it. And most of the chips are made in digital. And we're going to have one on and off. So CMOS, another advantage is on and off, 2 switches we make. That's why we use CMOS. So indirectly, 2 ideas. No, you cannot. It's very difficult to reduce the power consumption. They have tried a lot. That's only finally they moved to FET. Today, all the ICs are made using FET. There is no BJT IC at all. BJT is used only outside for amplification. We don't use the BJT for inside that ICs. Okay, even the CMOS FET itself, so many things they're called FinFET. There's so many new technologies have come. They were all ultimately I have to make a switch on and off. Finally, when they're going to say one day, I'm going to control 1 electron. 1 electron I'm going to make about. See, now think of it. A transistor is made at the size of 2 nanometer. Think of it. 1 meter, 1 by 100 is milli, 1 by 1000 is milli, 1 by 1 million is 1 micro, 1 by 1 trillion or 1 billion is called 1 nano. So today, they make a transistor at the size of 1 nanometer. That's why they call right now 2 nm. They are trying to work on 1 nm. Such a powerful technology. But don't get confused. We are going to discuss about how. See, the trick is that you should go up. Don't stay here. Don't stay here. Go up. I want you to learn, understand. At the same time, you have to go up. If you don't go up, you will never catch the 2022. That's a problem. If you go at the same speed of this guy, you will take 40 years to catch up this. 40 years back only, the 1947, the transistor was invented. How many years it took? You also want to spend the same time to learn it? Electronic currency works. Yeah, we will discuss about that later. For that, you should know about networking. Okay. You have to know about Bitcoin. Those things are all, that's actually a fundamental called blockchain. The beauty is this. Let me tell you one more beauty. Why I discuss all these things. If you understand fundamentals, and in our embedded system class, we give you the full architecture. If you understand 100% of our lectures, you don't have any doubt. You will be able to understand networking. You'll be understand IoT. You'll be able to understand blockchain. You'll be understand the software. Everything is possible. Everything. But this gives you the full fundamentals. We discuss about fundamentals. So there are transistor. There are two types: BJT, FET. The BJT is a current controlled. FET is voltage control. BJT two type: NPN, PNP. In FET, MOSFET, JFET, junction FET. This initially came, then MOSFET. They have the semiconductor. So metal oxide semiconductor. Then there are PMOS, NMOS, P channel, N channel. They combined both and created CMOS. Okay, so if you'd like to have more doubts on these things, write whatever doubts you have it and send me the message as a WhatsApp. I'll create all the doubts. And it's called junction field effect transistor. It came initially. Then it explained about there's a unique junction transistor. Then it'll take more time. I get into the too much of FET. That's why I just went into exactly the application of MOSFET. We don't use them. It's all gone nowadays. All of them are gone. That's all today. CMOS is a technology, and then that's gone very big. Maybe I told you I'll start the analog electronics. Just watch them. I think I might have explained that, Jaifit. Okay, then let me. So this idea, don't go in depth. See, if you go in depth of this is, you know, one thing. Most of the, let me stop the recording.